Good morning. Welcome back to the webinar series by IEEE MTTA PEMC Joint Chapter at Research Institute for Microwave and Millimeter Wave Studies at NUST H12 Campus, Islamabad. I'm Dr. Noshirwan Shoaib, Chair of the Joint Chapter. I welcome you all at this webinar. Today, we are pleased to welcome Dr. Hassan Khan from Hassan Habas from University of Glasgow. His talk title is Plasmonics enable super resolution microscopy techniques. Dr. Hassan Tahir Abbas is a lecturer at the James Watt School of Engineering, University Glasgow, UK, and also affiliated with Glasgow College UESTC, China. Previously, he worked as a postdoctoral research associate at the Center for Remote Healthcare and Technologies, Qatar, at Texas A&M University at Qatar. He obtained the PhD in electrical engineering from Texas A&M University, the USA, in 2017. Dr. Abbas has contributed to more than 25 research publications, 3 book chapters in some of the leading journals, and peer review conferences in the field of plasmonics and electromagnetic theory. He has vast experience of teaching graduate level courses for which he has received several awards of excellence. His research interests are plasmonics, EM theory, and wearable medical devices. He is a member of the IEEE and executive member of the IET EM Technical Professional Network and serves as a reviewer for several prestigious journals in his field. So without any delay, I request Dr. Hassan to please proceed. Over to you, Dr. Hassan. Thank you.
Thank you very much, Dr. Noshirwan. Uh, Good morning, good afternoon, wherever you are. Hello, everyone. So today, I'd like to talk about a topic which is entitled Plasmonics-enabled super-resolution microscopy techniques. Just to give you a brief background, as Dr. Noshirwan suggests, that I am a lecturer at the James Watt School of Engineering at the University of Glasgow. Currently, I am seeking master's level as well as PhD students who are interested to work in the field of electromagnetic theory as well as device fabrication for the applications of plasmonics and nanophotonics. So to start the talk, I would like to present first a brief outline of my talk. It's basically revolving about the developments of microscopy, and we'll basically talk about a historical review in the beginning and slowly the progresses that have been made throughout the history. And more recently, we will be talking about the emergence of the field which is called as nano-optics. And in the nano-optics in particular, we would like to talk about a field called super resolution microscopy. And then further over there, so we would like to talk about a particular type of microscopy technique which has been gaining a lot of interest in the past few years, owing to its ease of use, fast speed, as well as ultra high resolution capabilities. So the history of microscopy, it dates back several thousand of human civilization. The earliest evidences of scientific observations and development in the fields of optics, the Greeks are basically here responsible for that. In the 1st century AD, there was an observation through a sphere of glass which was filled with water, and when that sphere of glass filled with water was put on things, they appeared magnified. So this was one of the earliest documented observations in terms of microscopic interests. And then as we move in time, uh, I think one of the major contributions were made in the golden age of Islam. Uh, a very famous scientist, I think we all may know about him one way or the other, Ibn al-Hashim. So he was responsible for laying the scientific principles for the propagation of light and some of the fundamental laws and principles in optics. He also formulated the structure of the human eye, which to this day is being accepted scientifically as well. And then as we move in time, the developments in science in all aspects of science actually, they were taken over by the European. So in the pre-Renaissance stage, we first witnessed the progress made by the Italians in the form of eyeglasses or eyewear for human beings. So that development happened in the 13th century, and as we move in time, uh, some of the like most important developments made in the field of microscopy were made in the 16th century by the Dutch. And there was the time where the resonance Renaissance movement was also uh, taking place in the whole of Europe. Uh, so for a few centuries, a lot of development was being made scientifically as well as commercially in terms of microscopes. And in the 19th century, some of the problems that were inherent uh, to the application and working of microscopes that limited not only the performance but limited its applications in a lot of fields. So those limitations were addressed scientifically by British scientists, particularly in terms of fixing the chromatic aberration that severely limits the performance of microscopes. So this is like a brief history, and then beyond this time scale, we start seeing modern developments in microscopy. So in terms of resolution capabilities of microscopic techniques, we see some trends in this graph that you see. So as you see in the left bottom of the graph, in the early part of the 20th century as well as the whole of the 19th century, uh, progress was being uh, dominated by the optical or what we basically these days call conventional microscopic techniques. And in the year around 1930, the first electron microscope was developed. And with the development of the first electron microscope, we see from this graph that the resolution capabilities they shoot it upward. So this is basically one technology change that happened around the 1930s that significantly advanced the field of microscopy. And then around 1955, we also see another switch or change in the science or principles of microscopic techniques. Then with the emergence of the scanning transmission electron microscope, we again see that there is a shift happening in terms of the resolution capabilities that we have these days. And now you see that towards the latter part of the last century and the beginning of this century, there is a lot of development in terms of achieving more and more resolution out of microscopic techniques. The ones the icons or the shapes that you see without the color, these are basically the ones in which uh, problems inherent to microscopic techniques such as spherical or chromatic aberration, they were starting to being corrected either electronically or through physical means. We also see that this is probably where we have a lot of stacking of developments. This is also in line with the emergence of computers. So as we had more powerful computers, we had more capabilities to somehow correct in terms of software all the inherent problems such as chromatic and spherical aberration that affected microscopic techniques. So basically, with the emergence of computers, we started to observe better imaging processing techniques that enabled us to have better imaging techniques overall. Now, as we have seen that the resolution of microscopic techniques have actually gone higher and higher, and especially in the last few years, there has been a lot of development. Now, not only we have seen development in terms of conventional optics, we have seen that the fields such as electronics and other fields which are plasmonics, which we'll be talking about in this talk, as well as photonics, in which we create different nanoscale structures and let the light actually play with those nanoscale structures. So with the development of advanced fabrication techniques, uh, in the last 20 years, we have been able to manipulate light in ways that have not been possible uh, in the history. So we have seen the emergence of new sciences such as photonics as well as plasmonics that help us manipulate light and which in turn can also be translated to the development of precise and super high resolution imaging of microscopic devices. So some of the super resolution techniques in which we currently deal with these days, they deal with the field of plasmonics. Now, to give you an insight about the fields of microscopy, we are physically limited by a problem called the diffraction limit, which says that the maximum optical resolution that we can obtain out of a conventional microscope, it is limited by the frequency or the wavelength at which we operate. Now, those conventional microscopic techniques, they are primarily far field in nature, in which we mean that if we interact with the electromagnetic field, that primarily happens in the far field. Now, with the emergence of super resolution techniques that are based either on photonics or on plasmonics, what is contrasting over here is that now we deal with imaging techniques in which the wave and matter interaction actually happens in terms of the near field. Or in other words, evanescent waves, electromagnetic fields, or the near fields, they come into play in these imaging techniques. Now, with these plasmonic or photonic based imaging techniques, we have been able to overcome or go beyond the classical diffraction limited, which actually limited the operation as well as the applications of conventional microscopic techniques. So in this talk, we will be looking at some of the super resolution microscopic techniques that are actually based on plasmonics. Now, before we jump into the plasmonic based imaging techniques, I think it would be probably wise to have a small discussion about the field of plasmonics itself. So this field actually developed in the last 20 or so years, uh, and this was actually being made possible by the advancements in fabrication techniques, which enabled us to interact with light as well as interact with matter in ways that were not possible before. Now, the main principle of plasmonics, it actually deals with nanoscale structures and their interaction with electromagnetic waves. Now, this interaction, it usually happens in at a sub-wavelength level. Now, what we mean by sub-wavelength level, uh, classically, the electromagnetic devices that we have, such as antennas, they are also somewhat limited by diffraction limit. Now, these plasmonic devices, the interaction or the waves propagate in such a way that it is actually much smaller as compared to what we would observe in free space. So that's why we call this interaction as sub-wavelength. And this interaction usually is only observed at material boundaries or interfaces such as the one that we see over here on the right. In the top figure, we see a metal and a dielectric. And at the interface, we see a propagation of a special kind of wave, which is commonly known as the surface plasmon wave. Now, surface plasmons, in short, they also exist in other interfaces as well. So primarily for optical frequencies, we use interfaces such as a metal or a dielectric. But when we go down in the frequency, let's say to terahertz, which is from 0.1 to around 20 terahertz frequency scale, in that frequency region, we observe these surface plasmons on the interfaces that are commonly found in semiconductor devices, such as field effect transistors and other devices that are made by similar fabrication techniques. Now, the observation of surface plasmons, it depends, as we just saw from this figure, that they depend on the choice of materials. And so this choice of materials will basically command or will decide at what frequency or what wavelength our system will operate at. Now, in order to have the existence of surface plasmons on material interfaces, there are certain conditions that we need to meet. So in the earlier slide, as I said, that there are some certain conditions that are either met at optical frequencies by metals and at terahertz frequencies by semiconductor materials. Now, those conditions are basically at optical frequencies. If we observe the dielectric of a metal, we would be looking at, or we would want actually, the real part of the Lightle constant to be negative in order for the surface plasmons to exist at the interface. Now, this negative part is commonly being observed by metals such as gold, copper, aluminum, as well as silver. So plasmonic based applications that work in the optical frequency range, they are primarily based on these metals such as gold, silver, aluminum, and copper. If we move to the terahertz frequency region, in the terahertz frequency region, we have a condition which says that the surface conductivity, it should have an imaginary part in order for the surface plasmons to exist. Now, this condition is actually as I said, that met by some semiconductor devices or materials. But most importantly, it is being met by two-dimensional materials such as graphene or transition metal triglycerides, which in general, those two-dimensional materials, they are these days called as van der Waal heterostructures. Now, the operation or the quality of surface plasmons, they are actually determined by a figure which we see on the bottom left. This is commonly called as the dispersion diagram. And in the dispersion diagram, we see that the further the curve is away from the light line, the more subwavelength capabilities it has. Now, if we observe surface plasmons in the optical frequencies, we see that we have some certain amount of subwavelength capability. But if we compare that capability with surface plasmons existing in the terahertz frequency range, the terahertz surface plasmons, they are much more subwavelength as compared to the optical counterpart. So this actually means a lot of things, but most importantly, it means that the confinement capabilities by terahertz frequency surface plasmons are much higher as compared to the optical frequency surface plasmons. So this will actually enable the development or the manipulation of electromagnetic waves to a much smaller scale. This particular feature is actually being used in imaging, which we will see in a short while as well. Now, plasmonics, they are primarily being championed by devices such as nanoantennas. Nanoantennas are primarily existing at optical frequencies in which we design some antennas which are actually scaled down versions of the microwave frequency antennas. It could be either a simple dipole antenna as we see on the right side of this slide, or it could be a scaled down version of a bow tie antenna as we see on the left hand side, or it could be either a Yagi-Uda antenna or any other antenna type that exists at the microwave frequency region. Now, in contrast with the antenna observation at microwave frequencies, nano antennas at optical as well as terahertz frequencies, they have a very unique feature. If we have an antenna at microwave frequencies, such as a dipole antenna, so the resonance performance will only be changing by changing the length of the antenna. On the other hand, in nano antennas, we can actually shift the resonance not only by changing the length of the antenna, but also with the width of the antenna, as well as by changing the material properties of the antenna with which it was built from. So we have actually now three dimensions of freedom through which we can actually control the resonance performance of these nano antennas. And this actually primarily happens because of the way surface plasmons exist at the surface of these nano antennas and how they radiate from the corners of those nano antennas. Now, those nano antennas or plasmonic devices, as we mentioned earlier, as they're existing at the terahertz frequencies, they are commonly found in semiconductor devices such as the one we see over here on the right top, which is a general schematic for a field effect transistor. Now, in general, a field effect transistor is made by sandwiching different semiconductors on top of each other. And when different semiconductors are sandwiched, we observe some unique electromagnetic wave phenomena happening at the interfaces. And this unique electromagnetic wave phenomena is actually the existence of terahertz frequency surface plasmons. Now, a unique feature of these terahertz frequency surface plasmons is that they can be tuned just the way we can change the electric biasing of this transistor system. Now, a special type of wave, which is basically nowadays called a Diakonov-Shore wave, or in short, a plasma wave, it was discovered about 30 years ago in these transistor structures. And it was discovered that upon some unique boundary conditions that are met in this field effect transistor, the waves trapped inside this heterostructure, they actually tend to radiate. And this phenomenon was basically then called as the Diakonov-Shore instability. And we also now know that whatever the emitted electromagnetic wave, the frequency of that electromagnetic wave can be actually tuned with the electric biasing of this transistor circuit. Now, in other words, we can say that this transistor circuit acts as an electronic flute in which just by changing the gate voltage bias, we can actually have multiple tunable responses of electromagnetic waves, and that especially in terahertz frequency region. And why it is important? It is important because there are a lot of established sources that we can find at optical frequencies. We can find very good sources which are very efficient at microwave frequencies. But until now, there has been a shortage of sources as well as detectors that operate in the terahertz frequency region. So this discovery of the Diakonov-Shore instability, which was discovered about in the late 1990s. So this opened up a new path of generation of terahertz generation as well as terahertz sensing. Now let's try to basically combine and aggregate what we have seen and try to see how they can actually be used or applied in developing high resolution microscopic techniques. So now we would be talking about a special type of microscopy which is called structure illumination microscopy. So before we delve into and discuss about the structure illumination microscopy, in conventional microscopic techniques, what usually happens is we have a sample stage in which whatever we would like to observe, we put that on the sample stage. And in conventional microscope, this sample stage is illuminated by a uniform light. Either it could be by uniform we mean that it could be an electromagnetic beam or a laser beam or an optical beam which basically has same distribution throughout its basically beam. So in other words, the beam can be described by an point spread function. So the point spread function is of basically of a Gaussian shape for these uniform illumination microscopic techniques. Now in this structure illumination microscopic techniques, what we do is, rather than having a uniform illumination, we illuminate the sample with a pattern illumination. And this patterned illumination is changed in multiple exposures. Or in other words, we take or we observe multiple snapshots of a sample with different illuminations. Now, when we post-process those images that in which we excited the sample with different illuminations, we see that the multiplication of these two different patterns, it actually results in a new pattern. So this actually is being observed in space, and when we observe this phenomenon in the frequency domain, so this multiplication is actually correspondingly a convolution in the frequency domain, and what is happening is we are actually enhancing or spreading what we are actually recording in terms of the frequency contents of the sample. So this observation is called the Moire fringing, and the Moire fringing, this overlap of different patterns in the space domain, this is observed as convolution in the frequency domain, which enhances this frequency domain observation space that we observe from a different microscopic technique. Now, with post-processing techniques, initially, if we would have been able to find out only this much frequency content for a sample, now we are actually able to find out an enhanced frequency content for a sample. And this actually would translate to much more sharpness as well as higher resolution for microscopic techniques. So this is basically a principle for structured illumination microscopy, where we try to illuminate the sample not with a uniform light, but with the structured light. And then that structured is reconstructed post in the post processing where an enhanced image is obtained. Now, some of the features that are advantages of this structured illumination microscopy technique is that we are still able to observe samples in real time. Now, this might be contrary to what we see over here, that we require multiple exposures, but we can change the pattern very quickly and we can actually reconstruct in post processing in very high with very low latency, which actually enable us to observe samples with very high resolution as well as in real time. Now, another very high benefit of this type of technique is, let's say if we want to observe some biological samples, usually if we put a higher intensity of light, that would mean a better performance or better image quality. But biological samples, they might be harmed or they might be intoxicated by higher intensities of light, just as we have limitations of using exposures to X-rays for us as human beings. Similar exposure limitations exist for nanoscale or microscopic biological samples for the limits of light intensities that they could bear. Now, this another advantage of structural illumination microscopy is that most of the features, it doesn't require much equipment, and most of the enhancement, it can be actually obtained while post-processing. Now, these are basically some demonstrations of structured illumination microscopy. The figure, the black and white figure, we see multiple exposures in which we observe multiple frequency spaces, which are actually in the end convolved to make an effective larger frequency space observation. Now, as comparison with conventional microscopic techniques, the figure on the right, it basically provides us a comparison of resolution enhancement. So this is a microscopic image for a biological sample. In the figure on the left top, we see what we would observe from a conventional microscope. And the figure on the right top is the one we would observe through SIM, which is short for structural illumination microscopy. So if we zoom in one subsection of the conventional microscopic image, so we would see a lot of blurred regions. And as compared to this conventional microscopic techniques, we see that there is probably a twofold resolution enhancement for structural illumination microscopic techniques. So now, moving on, structural illumination microscopic technique, it was primarily proposed to work in optical frequency domain. But with the advancements of the field of plasmonics, particularly in the last 15 years, we saw more and more plasmonic devices being used in which we can illuminate the structure. And some other interesting applications were also proposed in the terahertz frequency domain. Now, the benefits of having a plasmonic structure illumination microscopy, especially in the terahertz frequency domain, is one of the chief one is that terahertz frequency, they are basically those waves are non-ionizing to biological samples, which means that any exposure as compared to optical frequency waves, it would not harm those biological samples. Moreover, the plasmonics that we have observed, especially at the terahertz frequency, the surface plasmons, they are much more sub-wavelength scale than the optical frequency surface plasmons. So this enables actually us to construct imaging techniques that actually provide resolutions which are much higher, which go actually much beyond the diffraction limit. So this is one proposed microscopy technique, which is made up of a semiconductor field effect transistor. We see that surface plasmons exist in this yellow region, which is the also called the two-dimensional electron gas or the two-dimensional material. Now this wave, more interestingly, in contrast with other structure illumination microscopic techniques. So this in this proposed method, we actually excite or illuminate the sample from the sample stage rather than having another external electric beam that is exciting the sample. So when this proposed technique is actually simulated, so let's say if we have a sample in which we have molecules spaced in this spatial distribution, the image that we would get from a conventional microscopic technique, it would be this blurred image and we see that we are not able to resolve closely spaced molecules. But through plasmonic structure illumination technique, we see that we are able to resolve those closely spaced molecules as well. Now, with these imaging techniques, the resolution is about 50 nanometers, so that we can go up to 50 nanometers easily. And moreover, the illumination, as I said, that is required to generate the patterns, that can be easily changed in this configuration by just changing the gate voltage bias. So we can quickly change the gate voltage bias, which will in effect create the different illumination pattern required for structured illumination microscopy. Now, these are some practical demonstrations of plasmonic structured illumination microscopy that actually have happened, been demonstrated very recently. And one of the unique aspects of this structured illumination microscopy, that it can obtain not only two-dimensional images, but three-dimensional images as well. So in order to have multi-dimensional imaging, such as two-dimensional or even three-dimensional imaging with resolution capabilities, we would require an illumination scheme in which we can somehow rotate or tilt the illumination pattern. Now, in this paper, in this project, what they proposed they proposed a set of waveguides in which the illumination beams has actually been split by an encoder. So based on this encoding and based on the way we actually excite the sample state through this multi-stage waveguide, we would actually have rotated illumination patterns, which in turn will give us resolution capabilities in 2 as well as 3 dimensions. Now, this is basically one demonstration that this paper made using excitation from plasmons from the sample stage rather than illuminating it from the top. Now, so this actually chart, this basically provides us a comparison of the capabilities of structured illumination microscopy, where we stand at the moment in terms of the resolution capabilities, in terms of what sort of light intensities we use, as well as the imaging speeds. Now, the imaging speeds, they have been going lower and lower because of the highly sensitive nature of the detectors that we have been able to observe lately. And moreover, more interestingly, this structural illumination microscopy technique has also been able to slowly give us 3-dimensional imaging capabilities in which we can get more information about depth as well. Now, the second figure, the one in the middle, it basically provides us an idea about the different types of illumination intensities that we use. Now, preferably, we would require a faster, higher resolution and imaging technique which requires a lower light intensity that does not overexpose or ionize the samples in a hazardous way. So we see that the illumination intensities for structured illumination microscopy, they are much lower as compared to other microscopic techniques for basically having an enhanced resolution image. Now on this, the right side figure, it basically shows us the resolution capabilities that we have so far. And just to basically give you an idea that this structural illumination microscopic resolution techniques, they are being enhanced more and more with the advancement of different 2D materials as well as different development of sensitive sensors through which we can actually observe all this interplay between light and matter. Now, just to have some conclusive remarks on this talk. So, what basically are the hottest topics that are currently being witnessed in the field of structured illumination microscopy? So, we should note that primarily the main benefit of this type of technique is the power of the reconstruction it has after we actually record the images. So lately there has been a lot of research interest in utilizing deep learning and machine learning imaging enhancement techniques for having much more better resolution. Now, one of the biggest, you can say, attractions of using such intelligent techniques for microscopy is that it would actually lower the requirements of the number of exposures that we require in order to construct a sharp image. So this is a very recent paper in which what these authors proposed is, just like in conventional machine learning, where they would have a training data set, and based on those training data set, they will train their classification model, and then they will apply that classification model on either different images or for any classification purposes. Now, in this paper, what they have done is that they have created a library of structure illumination microscopic images through which they have trained their deep learning model, which is based on a neural network. Once they have trained, then they can actually reconstruct structured images which would require much more less number of samples images for reconstruction. So this is basically one of their demonstration that they have made. So this one on the animated figure on the left that you see is what they would observe from a conventional microscopy, and using their reconstruction deep learning algorithm, they actually were able to reconstruct and pick out, resolve much more details in their images, not only in real time, but with much less number of recorded samples. So the attraction of this is basically the less number of exposure samples that we would require, and that will actually enable us to have even more faster structured illumination microscopic techniques, which will even actually now we are able to image biological samples live, but these sort of advancements they will actually enable more to have much more clearer picture in future. And another very interesting area of interest that has been emerging very recently is, rather than having illumination pattern applied throughout the sample, we only apply the illumination sample at a particular localized point in the sample stage. Now what it does is we can then change the point of localization, and by changing this point of localization we can scan the whole region. So although this type of imaging technique is slower than the plasmonic structure illumination microscopy, but this truly is actually a nanoscopic technique rather than a microscopic technique, because the features that we are able to resolve through this localized structure illumination microscopy technique, they are much more enhanced. So in this paper, the authors actually demonstrated a resolution up to 20 nanometers. And what they propose is, based on the way they illuminate the patterns, they can actually go to molecular levels, which is about 5 nanometers resolution levels. So this is basically two very interesting areas that are recently developing. If somebody would like to have an interest in this imaging techniques, so this basically is a combination of electronic devices as well as semiconductor devices. So what you have seen over here is basically that the recent fields that are emerging, they require multiple dimension of skills. So if let's say if you are a student, so now is the time to develop skills that are multidimensional. So you would have seen the application of deep learning or machine learning everywhere. And this is one prime example of application of deep learning, which is gaining a lot of traction in the past year, that how to reconstruct super resolution imaging techniques through deep learning. So I will stop now, and if you would like to know more about structured illumination microscopy, uh, I would encourage you to contact me on my email, which is displayed on the slides. Thank you very much. And if we have any questions, so now we can have a round of questions. Thank you.
Thank you, Dr. Hassan, for a very informative talk. There are a few questions lined up, so I will ask you one by one. The first question is how the design of a plasmonic nano antenna different from a typical RF microwave antenna.
So as we looked at, so so one of the things that has to be kind of clarified, which is a misconception, is a plasmonic nano antenna is more like a sensor. So what it does is it helps other nanoparticles to radiate rather than it being radiating itself for communication purposes. So we could think of a plasmonic nano antenna as an assister rather than a direct radiator. Now, the differences in terms of design is basically for microwave frequency designs, we are primarily interested in changing the dimensions. So let's say if I talk about a dipole antenna, so the only dimension we would be interested in changing would be the length. For a patch antenna, we would have length as well as the width. But for a nano antenna, not only we have dimensions such as width and length, we also have a freedom to change the material properties by changing the conductor itself with which we construct the nano antenna. So by changing the material, we could also change the design, which is in stark contrast with radio frequency design, where we just treat all the metals as perfect conductors. So this is basically one primary or chief contrasting feature of nano antennas.
Thank you very much. There is another question. This is the first time we have heard about plasmonics. Our study of plasmonics or part of a graduate curriculum. What resources do you recommend for this branch of science?
So that's a very interesting question. So this plasmonics field, I would say, quickly developed in the last 20 or so years. And that was actually being made possible by the excellent developments being made in the device or semiconductor fabrication techniques, that now we are able to manufacture patterns that are basically uh, could be of nanoscale. So we could have a desired pattern which was not possible 20 years ago. So to take up plasmonics, it could be actually from two dimensions. So let's say if somebody is having a major in physics, so they could come from a physics side where they would have the quantum effects of they would study the quantum effects of plasmonics. But for engineering students, it's basically a step forward from conventional electromagnetic field. So all the basic principles of electromagnetics, they apply, and they can actually translate it to electromagnetic fields. So most of the fundamental principles of plasmonics, they could be very well understood by uh, uh, simply Maxwell's equations. So for engineers, I'm also an engineer. My approach to plasmonics is from an engineering side, which is basically just studying it from a Maxwell equation point of view. For resources, there are some excellent books that came out in about past 10 years. One that comes into my mind is a book called Principle of Nano Optics, which is being written by Professor Lucas Novotny. Uh, and those actually books, they came out of their experiences of teaching graduate courses. So for graduate students, they are very helpful, and they are very insightful because those are actually translated versions of lecture notes, I would say.
Thank you very much. I think there's another question which is, I may think, related to the previous question, but I'll just repeat if you would like to add any other point. In order to study and understand plasmonic, it seems knowledge of particle physics is necessary. How do you think in an RF or electric engineer address this knowledge gap or deficiency in understanding plasmonics?
So again, as I said, there are two aspects in which we can actually look into the field of plasmonics. One is from a physics major point of view, where we would be interested in studying the particle physics and more appropriately the quantum mechanics of whatever is being observed. But for an engineering student, as I mentioned earlier, that all the fundamentals of plasmonics, they can be well explained by just studying the Maxwell's equations. So through Maxwell's equations, we could explain the subwavelength phenomena. We could explain how we actually obtain electromagnetic waves out of those plasmonic structures, either they are nanoantennas or any other plasmonic devices. So basically, it's just an extension of electromagnetic theory, and I would stress that it does not require uh, knowledge of quantum electrodynamics or quantum mechanics to actually delve into the field of plasmonics. Just the basic understanding of electromagnetic theory will suffice.
Thank you. The next question is, can you please highlight few examples of plasmonics for next generation 5G wireless communication system?
So this actually, I would say, is a little far away, because for 5G communications and even probably 6G, we might not reach the terahertz frequency region. For 5G, we are currently looking at either just the 6 gigahertz frequency spectrum, or the millimeter wave frequency region between 27 to 28 gigahertz frequency region. In that frequency region, we have the conventional microwave devices that perform really well. Uh, and the biggest challenge for plasmonic devices is that they primarily are currently efficient only in near field. So even if we have communication devices made out of plasmonic devices, they would be done in the near field. So in terms of communication aspects, maybe in 6G or even beyond, we could look at applications such as we have sensors that are embedded into our bodies, and those sensors, they actually transmit some vital signs through Plasmonics onto some sensors that are available on our skin. So this is the type of communication that we can imagine out of Plasmonics. Since they are mentioned, as I mentioned, they are sub-wavelength devices. So any communication that has to be done, it will have a very limited range.
Thank you. Maybe this is the last question. Can you please highlight the fabrication and characterization challenges for plasmonic devices?
Yes. So now, even with the rapid developments, let's say, of device fabrication techniques such as molecular beam epitaxy or MOCVD, uh, we for plasmonic structures, uh, proposing them in terms of simulation is one aspect, but actually fabricating them is another aspect. So let's say if we want to fabricate a dipole antenna, in simulation, it would just be modeled as a cylinder. But when we actually fabricate it, that that cylinder, it will actually have maybe shapes which is quite irregular, especially at the ends. So from an electromagnetic field standpoint, uh, if let's say if a smooth dipole antenna was radiating at X uh, terahertz or X gigahertz frequency range, some irregularities in the structure that would actually change the response slightly. So we are not at the point where we have a precise or smooth uh, fabrications of nanostructures. There will be some imperfections, and those imperfections actually result in some change in electromagnetic behavior.
Thank you very much, Dr. Hassan. I think due to time limitation, we have to stop now. So if the audience have any question, they can directly write to Dr. Hassan. In that, I would like to thank Dr. Hassan for your very interesting, informative talk. I would like to thank you for your time, and we hope we will see you again at some later forum as well.
Thank you very much, Dr. Noshirwan, for the kind invitation, and I hope this was stimulating to the audience. And I know that there is an anonymous question in the chat. So, Dr. Noshirwan, if you may allow me to just kind of quickly address that anonymous question.
Yeah, sure.
So there's a question which says, does this technology play a role in medical field? Are there adverse effects on human body of plasmonic nanotechnology? So for plasmonic, especially the structured plasmonic structure illumination microscopy, the benefit is that the exposures that are required to obtain images, they are substantially lower as compared to the conventional microscopic techniques. So all those basically hazards or exposures that could be concerning, they are related to the intensity or the frequency. Now, as these techniques are there, they're basically primarily low intensity, so they are not very hazardous or they don't have any harm to either humans or even biological samples in general. So I hope this answers, and thank you very much, Dr. Noshirwan, once again for this kind invitation and opportunity for sharing the research, and hope to see you again in future as well.
Yeah, sure. Thank you very much for your time and the talk, and inshallah, see you again at later forums as well. Have a nice day, and for today, bye bye. Thank you very much.
Bye bye.
Bye.